Good. All right. So thank you everyone for joining us. So this is the research Bytes session for Galaxy Morphology. So we have 4 talks, as you know. So each talk will be 3 minutes each, and then we're going to have a 10-minute Q&A where you can ask questions. You can put your questions to any of the presenters. So let me just take you through some of the introductory slides. So I guess you guys have all seen these slides before at some point. So I'm not going to spend too much time on it. So we have a code of conduct, which we expect everyone to adhere to. So obviously any discriminatory behavior against colleagues on the basis of any personal characteristic is not going to be tolerated. And so if you witness any form of bullying, harassment, or aggression of any kind during this meeting, please feel free to send me or Benne a message on Slack. And we will take appropriate action. Okay, so all the talks at this workshop are being recorded. So if you would prefer not to be recorded, then please mute your mic and your video. The videos will be posted the next working day. Feel free to use the thumbs up and the appreciation emojis that Zoom provides. So in terms of the questions, please put your questions either in the Slack channel for this meeting, or you can also use the chat option in Zoom. And Benne, as I said, will keep an eye on the questions, and he will essentially collate your questions, and then we will have a Q&A at the end after all the talks have been done. Okay, good. So without further ado, let's begin. So our first speaker is Lior Shamir, and he will tell us about using Rubin for identifying cosmological scale patterns of parity violation in galaxy spin directions. Over to you, Lior.
All right, thank you. So my idea is rather provocative. We know that galaxies, the disk may spin one way or the other way. We tend to think that it's random because it's just a matter of perspective of the galaxy, the way we see it from Earth. So it just makes sense to assume that for a large number of galaxies, the number of the spin direction would be more or less even, statistically even. The problem is that we have some data that suggests that that might not be the case. I have this small example from Sloan, about 64,000 galaxies. You see that it changes based on the direction of observation. It changes with the redshift. So the patterns is fairly consistent here, and there are more experiments, more data from Sloan, from Penn stars, from the border Hubble fields like Cosmos. You have the same uneven distribution. So that might require further investigation. Vera Rubin gives us much more data, more sky, better data can answer that question. Next, please. And you might have seen the idea of dipole and quadruple alignment from the cosmic microwave background at cosmological scale. The asymmetry of galaxy spin directions also seem to give similar patterns, or can be fitted into similar patterns of dipole and quadruple. Again, with Vera Rubin, we have more sky, more data, it can better answer that question. Next, please. Next slide. Yeah, thank you. Here I have some one example to justify the effort to look into Vera Rubin. So I have 2 completely different data sets, orthogonal data set of galaxies. And you see that also in Sloan and Penn stars, they both show symmetry, but it's not just they show that the number is uneven. The distribution, the pattern of distribution is consistent. And you see one is from Sloan, one from Penn stars, different galaxies, completely orthogonal data sets. From completely different instruments, but the pattern is fairly close, and that's when talking about 2 different instruments, that's as close as you can get. Vera Rubin might be able to give us more data, more answers about that provocative observation. Thank you.
Okay, thank you very much. Nushkia, is your internet working?
Yeah, can you hear me fine?
Yeah, we can hear you. Okay,
okay,
great.
So
okay. Our next speaker is Nushkia Chamba, and she will tell us about the size of galaxies in an era of ultra-deep imaging.
Okay, great. Thank you, Sugata. So in this figure, I'm showing you a few galaxies, an M87-like elliptical galaxy, a Milky Way-like galaxy, an ultra-diffuse galaxy, which is a low-surface brightness galaxy, and a dwarf galaxy. And these are all shown to the same physical scale and using images of the same depth. I'm using Deep Stripe 82 data here, which has a limiting depth of 29.1 magnitudes per arcsecond squared in the G-band. So when you have an image like this, you may ask the question, what are their sizes and how can we compare them? Because intuitively, you would think that the sizes of these galaxies are related to their boundaries. Next slide, please.
Oh, sorry.
Yeah, that's fine. And this is, oops.
Is this the right one?
The previous slide, the previous one.
So you want the previous one? Okay, sorry.
Yeah, so that was the second one, yeah. Right, so, and this is because even historically, the size of galaxies was defined using isophotal size measures, and this was because they wanted to measure the maximum galaxy diameter. So for example, Redman in 1936, he defined D25, which is the isophote at 25 magnitudes per arcsecond squared. And this was based on the limiting depth of the photographic plates he used. And here I've also overplotted where the isophotes of these galaxies look like. In the next slide, please. But today, most of the works use the effective radius as a galaxy size measurement. And the effective radius is defined as the radius which encloses half the light of a galaxy. This was defined in 1948 by Divaculas, and he used it basically to parameterize a light distribution model for elliptical galaxies. And even at that time, the effective radius was understood as a measurement of the light concentration in galaxies. So as you can see, I've overplotted for these galaxies where their effective radii is, and they mostly are in the center of the galaxy because it's following where the light is most concentrated. And the effective radius has been used also to compare the sizes of galaxies. And one example is that the ultra diffuse galaxy, because it has effective radius similar to Milky Way-like galaxies, has been interpreted as having Milky Way sized. So the question is this a representative measure of galaxy size? Next slide, please. So for my work, we redefine galaxy size with a physically motivated parameter. The reason I say that is because all the previous size parameters I introduced earlier were not based on any astrophysical idea. It was based on models and observations. So we define a size based on the radial location of the gas density threshold for star formation. And in this work, we explore a proxy for this threshold, motivated by the typical density of the truncation of Milky Way-like galaxies. This is at 1 solar masses per parsec squared in stellar mass density, and the radius at which that occurs, we call it R1. And two main results that I'll tell you in the R1 which we studied over 5 hours of mass.
Nushkia, you're cutting out.
They are upsized.
You might want to repeat the last couple of sentences because you cut out a bit.
Sorry, the results. So one result is that the scatter in the R1 stellar mass region, which we studied over 5 orders of magnitude in stellar mass, so going from dwarf regime to elliptical galaxy regime, is 3 times smaller than with the effect radius as a size measurement. And the third result that I'm telling you here, find that ultra diffuse galaxies are Milky Way size and dwarf size. Was that clear?
Okay, thank you, Nushkia. So next we have Cristóbal Moya, and he will tell us about morphological measurements with DRE.
Okay, thank you very much. So DRE, Discrete Radius Ellipticals, is a new algorithm that we have been working with. What we want to do is to obtain fast morphological measurements on large imaging datasets and do it as fast as possible. So this algorithm, instead of building a model from scratch, we start with a library of available models and we feed all of those simultaneously. So all of the results, the preliminary results we have gotten have been from BST Atlas survey imaging. So in this figure, I showed you this cube of models that we start with. So we have these three indexes, three axes, which are the effective radii, the axial ratio, and the position angle. So you have three indexes, I, J, K, and each set of indexes will give you a unique de Baculers model for each of these parameters. Next, please. So, yeah, okay. So how does the algorithm work? Okay, so first we pre-process the data using Sextractor and PSFX. Next animation. Okay, so we with the PSF, we measure the PSF in our image and we convolve that with our set of models. Then next, let's say we take a example galaxy, for example, that one. What we will do is each model is subtracted from that galaxy. Next, and we will end up having a cube of residuals, something that looks like that. Then we can measure those residuals within the Sextractor segmentation mask, and we will end with a cube of chi-square measurements. Next, something that looks like that. Right. So then we can, for example, say that the model that best fits our data is the one that minimizes the chi-square. Next. Here you will have, so we have this example, I mean, this input galaxy, we have the segmentation mask, the model, and the residual. Okay, next. So the current status of the, oh, sorry, first some pros and cons. So it's computationally simple. You're just doing a lot of matrix operations, and given that it has this tensor-like nature of the problem, it's a great candidate for GPU power up. As a con, a couple of cons is that this is heavily dependent on Sextractor for all the pre-processing. Also, it's limited by the density of models. By density of models, I mean how many models can I fit in my cube, and how many models do I have between each parameter. As a work in progress, we are quantifying the effect of the PSF variations, interpreting the residuals and defining meaningful quantities from them. Also injecting and recovery models to see what the pipeline is doing. And as a prospect, we want to use this to isolate a sample of early type galaxies, because the idea is that those galaxies will have better fits than late type galaxies. And by finding a lot of early type galaxies, we hope to find galaxy clusters. Thank you.
Okay, thank you, Cristóbal. And our last talk, so last but not least, is Preethi Nair, and she will tell us about a new visual morphological catalog of 113,000 galaxies.
Hi, everyone. So I was hoping my last catalog of 14,000 galaxies would be the last major catalog I would have classifications, but it turns out to not be enough to address a number of problems. And I just bit the bullet and classified all galaxies in SDSS. It should be DR7, but with redshifts between 0.02 and 0.06, with stellar mass between 10 to the 9 and 10 to the 12. And so that's about 113,696 galaxies. A lot of these galaxies also have NOAO Legacy Survey imaging. These are the deeper imagings that have come from decals and MZLS BAS. And the goal here, what I really wanted to do was really nail down the number of bar galaxies that you have. And I was also very interested in low surface brightness features and dual nuclei. So here I'm showing some images. You'll see a post-merger galaxy. It's a remnant with tidal tails and shells, just a representative system. You'll see this, the next system, which shows two agents that are interacting, and you see two nuclei. SDSS has a problem in getting spectra for both nuclei in these type of systems. So I wanted to find those. You also have these really interesting systems at the bottom where you see a central really bulge dominated system, and you have a low surface brightness star formation, accretion, something all on the outside. Now these systems tend to be quite rare. There are only about 80 of them out of the 130,000 systems, but I had some in my original sample. So I wanted to find them. And then normal bars, rings, spirals. Next slide, please. So there are a couple of things that I'm doing with this, aside from actually looking at close, what bar fractions are and things like this. One of the things that we really want to use this for is to calibrate quantitative morphology measurements. I have a student who's working on this. The other is to actually verify current public morphology catalogs, either visual morphologies like from Galaxy Zoo or through machine learning algorithms. The table here is just showing examples of, I'm just giving an example with Galaxy Zoo here, and you can look at the first in green. If you use the bar probability greater than 0.8, you will get 81%, the 81% of the sample that you find are in fact barred. But you only get 31% of those galaxies that I say are barred. And so that threshold, this accuratest completeness and contamination, it varies based on the Galaxy Zoo probability, and it also varies on stellar mass. This is also true for the Dominguez-Sanchez catalog. And a number of people, as clearly as Galaxy Zoo says how the catalog should be used, people don't use them as they should. So it's to verify these other catalogs. Last slide. So again, this is really quick. So one really cool little example that my student Kavya Makandan is working on. This is looking at bar fractions in the local universe, and she confirms that bar fractions are bimodal, just like I originally found. But what was the cool bit is we looked at these surveys in bar fractions that overlap with alfalfa. And on the left are galaxies that have a detected measure of H1. And the right are galaxies that do not have a detected measure of H1 and H alpha. And the bar fractions overall are really quite different. And so we're coming up with interesting trends there. Thank you.
Okay, thank you very much to all our speakers. Thank you for sticking to your 3 minutes. So I think we are running about 2 minutes ahead of schedule. So I'll stop sharing my screen and then we can move to taking questions. So over to you, Benne.
Okay, so I have 2 questions so far from Ilsan Jung. Nushkia, how do we measure the R1 in observation? That was a question I had as well.
Yeah, so I'm using stellar mass density profiles. So what we did was we measured the surface brightness profiles in 2 colors, and then we get a color profile. And from that, we convert that color profile to a mass density profile. It's there in the paper, exactly the conversion we do. And then from that mass density profile, you can find out where the threshold is.
Do you use the prescription? Like, gosh, sorry, I can't remember what the...
You mean for the conversion?
Yes.
D minus R. We're using the color to stellar halo, stellar mass to light ratio relations. This is a linear relation from the Rodiger and Curto 2015 paper.
There's several out there. That's what I was curious about. Which one you were using? There's a Zibeti one as well. Okay, and the second question I had for Vasquez, you have to be careful with early galaxies in deep images because most of them have LSB structures around them, like tidal structures, like rings, etc. Are you taking that into account into your modeling? Sorry, this is for Moya.
Okay, sorry.
Repeat the question. Hi.
Yes.
So LSB structures, and with the case of the Vera Rubin Observatory, you're going to see LSB structures around them, like rings, etc. Are you taking LSB features into account into your model?
As of now, not. All of our models are just simple the baculars models. But eventually we want to expand to having different input models for our set. But yeah, right now we are only fitting early type galaxies, only fitting bulges.
I had a question about this one as well. Are you planning to expand to disk galaxies as well, or is it ellipticals only?
That's something that I would like, and it shouldn't be hard because we will only need to change the CERSIC index in our input models and then do the same thing that we're doing. Yeah, that would be a next step.
Okay. And how is it depending on source extractor? I perked up at that.
Sorry, because so the input models are just the Baculers models right now. So, and they have three parameters. So when we build those models, so okay, we do a for loop, and we have a different the Baculers model for each entry in the array. So what we have to do is to change the input model for each cell in the array, and we will have like a new cube of models. So we could build a cube of spirals.
I understood that. It was more of a, you said it was very dependent on source extractor. Is it because of this, whether or not objects get broken up, or how much of the data gets included?
No, sorry, I don't quite understand the question.
You had a con in your pro and con slides. You had a con. It depends strongly on source extractor, because the source detection.
Oh, no, on sextractor.
Yes.
Right. Why is it so dependent on sextractor? Sorry. Okay. Because we use sextractor for all the pre-processing as of now, and especially to do the segmentation mask, because all of our measurements are done within the segmentation. That's a con because we don't have as much control as we would like in tuning in what we are doing with sextractor, and also there has been some unexpected behavior with those masks. We have gotten some masks that are like broken up, like some discontinuous mask, and that's troublesome. Yeah.
Okay. Well, thank you so much.
Thank you.
I have two questions here for Preethi. Yes. Okay. So first one from Gareth Martin. If I understood, you are using complementary data with deeper imaging in some cases. If so, how do you deal with quantifying the low surface brightness features, given there is a mixture of depths in the imaging?
So in one case, I would have to say most of the galaxies that I was trying to find, so the post-mergers were the first things. I found most of them with SDSS. The features are fainter than what you would get in NOAO Legacy Survey. There are some in NOAO, so there are about another 100 in the Legacy Survey that have added onto the sample. So the majority are falling in there. It is true. So this is one of the reasons I still need to characterize the surface brightness limits down to which I can find these features. The extents may not also be the same in the NOAO Legacy Survey versus the SDSS. Like the details might be missing, but the goal was just to find them first and then characterize their surface brightness. That's actually a harder problem in many senses. But the goal was to see how would you compare the two surveys. And in the catalog that I'll finally release, and again, I won't release, because I want to verify other catalogs. My goal is that from this 113K, I'll release a significant fraction, but I'm saving. I have to figure I'm saving a certain fraction, and that's going to be like everybody else puts out their results and it's a blind test. I'm the only one who knows what, I mean, if people use my classifications to train their algorithms, then it'll be compared against my blind sample that no one else has access to, just to see, how well they're really doing. But yeah, so it is a problem that there will be a mixture of depths, but I'm finding most within SDSS as long as you're using DS9 and playing around with the surface brightness contrast.
So that'll be a sealed envelope.
Pretty much, yeah. Like CERN and things like this, right? It drives me crazy, and that's a long story. We won't go there. But.
Okay, well, we have a second question for you, which is why bar fractions has a correlation with H1? Is it because the bar funnels the gas? So some of them are detected and some of them are not in your two plots.
So this is something that Kavi and I are still investigating. So there's an expectation on, if you have gas, how stable the disk is to bar formation. And the most simulations predict that you have more gas, it delays bar formation. It delays, the expectation we wanted to see was how it affects the size and strength of the bars. That it might delay bar formation, or it could, in fact, it depends on mass range. And so for the galaxies that have measured H1, there's a mass dependent trend on if you have more gas. For high mass galaxies versus low mass galaxies, the presence of gas actually affects bar fractions in different ways. But then if you look at all galaxies that were not detected by alpha with this blind survey, down to the limits that they have, the overall bar fraction in that sample is just lower. So It's like 14% if it's a non-detection, and if there is H1, any detection, then the bar fractions average is like 40%. And so we're investigating to see if it's maybe due to environment or something else, but right now it doesn't seem to be environment. But this is ongoing.
And Sugata has one for you, has another one for you. Do you see the LS, the low surface brightness tidal features around galaxies at the lower mass end of your sample, so 10 to the 9?
Yes, you do. Again, I haven't quantified the strength, and it really depends. And the main thing is that I've said everything is I put everything under the category of tidal tails, shells, fans. It's one, so I click a single box right now, and the goal eventually is to try to tell the difference between them. And so the shells are more common in more massive galaxies. Tidal tails are present across the board. And I do know Karen Master's paper. That's she's a co-author on the paper that we're working on right now with Kaviraj.
Yes, that's what Karen just sent around. I'm checking Slack as well. Yes, for Cristóbal, what is the benefit of pre-computing the full grid of models if it's to evaluate all of them in parallel? Otherwise, it might scale badly. 3 parameters is for 512 models for a very coarse 8x8x8 grid, which is more model evaluations than you'd normally need to minimize chi-square in serial. So, Cristóbal, do you want to take that?
So the advantage is that so the convolution is probably what takes most of the time when doing this. So what we're doing is moving the convolution out of the algorithm and into the pre-processing. Also, another advantage of having this grid is that you can do this in a parallel fashion. Also, you can, as I mentioned, this has the potential to be a good candidate for GPU computing, which my first tries with that have been positive, but still working. But those are the advantages, that you are not doing a convolution for each model, rather than just convoluting all of the models just one time, and that it has the potential to be parallel, to be a parallel algorithm.
Okay. See if I got any more questions. Nothing on the Slack, and nothing on the. Okay, that's everybody's question answered, I think. Sure. I have a question for Shamir. Which filter did you determine the spin factor in? How do you do that? Is it tracing spiral arms, or how does that work?
Oh, well, that's a long story because I use several different methods, several different data sets. Some I actually analyzed manually, actually one by one for several months, some of them. Most of them for the bigger one, because I have some data sets of several 100,000 galaxies, that I used an automatic algorithm, a model-driven algorithm that I use for it just converts the galaxies to the radial intensity plots and then analyze the radial intensity plots. So it's fairly accurate in identifying the spin direction. And I also used, actually I used for some, I also use like those deep learning algorithms, but for question like this, I just don't trust deep learning to do something like this, even a small bias, because we're talking about like 2% bias, things like that, for a large number of galaxies. So I don't really trust, I don't believe that deep learning algorithms, that's the right approach to handle a problem like this. So I use them, I just don't trust the result, that the bias is too high there. So I use the either manual analysis or model-driven analysis, depends on the size of the data set. And sometimes I use both and compare the results just to make sure that it's consistent. But there's a lot of work on that analysis thing.
Okay. Who has more questions? Do we have more questions? I can always come up with more, but I pose it to the group.
Benne, I think Melissa suggested transition time at 11:15. So that's still 15 minutes away. I think we started more or less on time, whereas some of the other folks probably didn't. That's probably why.
Well, I got answers to just about everything I've got here, so I'll start making up questions. Otherwise, it's just.
I mean, we can also stop and have a longer break if I think that's fine too. Pat, I don't know if you have any thoughts on what we should do, but.
Right, yeah, some of you might be oblivious to the fact that there are a lot of technical issues. I think there was a limit of 5 rooms that could be open at once. Zoom actually has a limit of, that might have been the technical issue, we'll figure it out, that you can only have 5 rooms under the same owner. So a number of the rooms had to scramble to get their own Zoom links. And so a number of the sessions started 15 minutes late. So we're formally going to start the next session at 11:15 and go for half an hour. That's going to eat into the next break. So what you might want to do is give people a break now, since they're going to get a shorter break later. And the chairs and myself, I dare not leave this room now. Anyone who's host and co-host, and plan to go to your next room at 11:15. And I think all the participants, if you really could try to get to another room, that would be great, because of all the confusion. We're hoping we'll still get a lively discussion going. So.
Okay. So I think we have one more question. I know we can probably get through that one, and then maybe we can break. People can break off.
Nushkia, are you there?
Yeah, can you hear me?
Yes.
Yeah.
The question was, how does the R1 correlate with RE, or effective radii, or does it?
Okay. To be frank, I didn't actually plot that. I never checked it because they're not related at all. They're differing and they're tracing different things. So the effective radius is tracing the central parts of most of the massive galaxies. And R1 is tracing star formation threshold. So I haven't actually checked whether they correlate or how, but I mean, the table is online. Anyone can download the table and check it. What's RP?
Oh, the Petrosian radius.
Oh, yeah. Okay. I mean, we did measure. So in the paper, we compared the dispersion and the slopes of different measures, so including the effective radius and also the half mass radius, and as well as several other isofortal sizes. And we show that comparison. And R1 is certainly tracing something very different compared to the other measures. But explicitly, I haven't checked how it correlates with the effective radius.
Cool. But your table's online. Is it?
Yes, so I mean, if you look, it's in the online material in the paper, so anyone can get it.
Okay. Sugata, shall we?
Yeah. So so thank you all again for coming. Sorry about the technical issues at the beginning. Please go to the next next room that you've chosen for the second half of the session. And thank you to all our speakers again for keeping to time and giving some terrific talks. So you can use, there's a clap emoji, I think, which you can use if I can find it.
And one more thing, so some of the Zoom rooms have changed for the next session, but if you go into the Rubin 2020 Slack channel, in the general channel is the updated Zoom links, and Melissa is in the process of updating the web page right now, the live web page. So when you get ready to join the next one in about 8 minutes or so, everything should be updated, and you should find the right Zoom number. Okay.
Thank you. Okay. Thanks, everyone. So speakers, please stay in this room, and the rest of you can go.
I didn't quite get the new time schedule.
Yeah, so
do we start again?
So we're basically running about 15 minutes behind because I think so there was this limit to 5 rooms, I think. So some of the sessions started late. So as far as you guys are concerned, you just stay where you are, and we'll just repeat what we just did in about 10 minutes time.
Okay.
But for people who are attending a different Zoom room, they will now have to check what the link is and go to the right place. Okay, good. Let's get going. All right. So thank you all for coming to the session. So as you probably know by now, we're going to have 4 flash talks, 3 minutes each, and then at the end of the session, we're going to have 10 minutes worth of Q&A where you can ask any questions you like to any of the presenters. So let's take you through some intro slides. So you've seen this already in the last session, so I'm not going to dwell on it. So please abide by the code of conduct. If you find any behavior that you find disturbing, then please send me or Benne a private message on Slack. Talks are being recorded, videos can be posted the next working day, and feel free to use the thumbs up and the clap emoji to show your appreciation for our presenters. Good. Okay, so without further ado, let's move to the first talk. So Lior Shamir is going to tell us about using Rubin for identifying cosmological scale patterns of parity violation in galaxy spin directions. Over to you, Lior.
Yeah, thank you. So the idea here is rather provocative. Galaxies have the spin, the disk spins, and we know the spin can be one way or the other way. And we tend to think that the spin direction is random because it's just a matter of the perspective of the galaxy from Earth. And so it makes sense that given the large number of galaxies, the spin direction would be more or less even, statistically even. But the thing is that we have some data that shows that that might not be the case. I have here this example from about 64,000 galaxies from Sloan, and shows that in different direction of observation, you have different population. The spin direction is not even. There's some parity violation there, and it changes with the direction of observation. It changes with the redshift. It's correlated to the redshift. This is just one example, but we have more examples from pan-stars and also from the broader field of Hubble Space Telescopes, all showing the same, very similar patterns, very consistent patterns of that sort of symmetry. Next slide, please. You might have seen the ideas of dipole and cosmological dipole and quadruple from the cosmic microwave background. The thing is that the spin direction symmetry is also aligned in the form of dipole and quadruple, and that is something that's examples from again from Sloan. Also, other surveys are showing that. With the Vera Rubin Observatory, we're going to have more sky, and we're going to have deeper and better images, much more galaxies to actually study that deeper. Next slide, please. And I also this example, so that's just a comparison between 2 sky surveys, Sloan and pan-stars. So both, not just that both show asymmetry between the spin direction of galaxies, the patterns of the asymmetry is very similar. These are 2 different instruments, 2 completely orthogonal data set of galaxies, and still the pattern that you see is still the same, given 2 different instruments. This is as close as you can get. So the question is whether the Rubin Observatory, will we see similar patterns also in agreement with Sloan and pan-stars? What are we going to see there? And that's the idea of the project. Thank you.
Okay, thank you very much, Lior. So our next talk is by Nushkia Chamba, and she will tell us about the size of galaxies in an era of ultra-deep imaging.
Thank you. In this figure, I've shown a couple of galaxies. This is an M87-like elliptical galaxy over here, a Milky Way-like spiral galaxy, an ultra-diffuse galaxy, a UDG, which is a low surface brightness galaxy, and a dwarf galaxy. These images are shown to the same physical scale and of the same imaging depth, down to 29.1 magnitudes per arcsecond squared in surface brightness from the Stripe 82 dataset. And when you see a figure like this, you could ask the question, what are the sizes of these galaxies and how can we compare them? Intuitively, you would think that the size of these galaxies are related to their boundaries. Next slide, please. And actually, historically, isophotal size parameters were used to do this, and they measured the maximum galaxy diameters. So this is an example here showing D25, which is the isophot at 25 magnitudes per arcsecond squared. And Redman in 1936 defined this size based on the limiting depth of the photographic plates he used. Next slide, please. And nowadays, most of the works use the effective radius, RE, as a galaxy size measure. This was defined by Devakoulas in 1948, and he basically parameterized a model to describe the light distribution in elliptical galaxies. And the effective radius was fixed so that it could enclose half the total light of a galaxy. And here I've also plotted it, and you can see that for the most largest galaxies, the effective radius is close to the center of the object. And this is because it traces the light concentration in the galaxies. And in fact, this effective radius is used also to compare different kinds of galaxies. And one example is that because ultra-diffuse galaxies have effective radius comparable to Milky Way-like galaxies, it has been interpreted that they are Milky Way sized. So the question is this a representative measure of galaxy size, and is the effective radius the right measure to do this? Next slide, please. So in my work, we have redefined galaxy size using a physically motivated parameter. The reason I say physically motivated is because the previous size measures that I introduced you were based on observational depth of the images or a specific choice in a model. So we actually base our size measure on the radial location of the gas density threshold for star formation. And in the work, we explore a proxy for this threshold, which we motivate by the typical density of the truncation of Milky Way-like galaxies. And for Milky Way-like galaxies, this occurs at 1 solar masses per parsec squared in stellar mass density. And the radius at which this occurs, we call it R1. So just two main results to show you the work. The first is that the scatter in the R1 stellar mass relation, which we study over 5 orders of magnitude in stellar mass, so this is exploring dwarf galaxies all the way to elliptical galaxies, is 3 times smaller than using the effective radius as a size measure. And the second result is that we find that the ultra-diffuse galaxies are not Milky Way sized, they are dwarf sized. Thank you.
Okay, thank you very much, Nushkia. So our next talk is by Cristóbal Moya, and he will tell us about morphological measurements with DRE.
Hello, everyone. So DRE means Discrete Radius Ellipticals, which is a new algorithm that we have been developing to obtain morphological measurements on large imaging datasets and do it as fast as possible. So far, all of the preliminary results we have gotten have been have come from the BST Atlas survey imaging datasets. So on this figure, you can see the models that we're using. So what we do is we have a library of available models. We build this sort of cube, and you have the 3 indexes, which are the position angle, the effective radius, and the axial ratio. You have 3 indexes, I, J, and K, and each set of those indexes will give you a unique Devakoulas model. So what we do is fit simultaneously all those models to a galaxy. Next, please. So how does the algorithm work? So first, we use Extractor and PSFX to get the segmentation mask and the PSF of the image. Next, the PSF is used to the models are convolved with the PSF of the image. Then next, for a given input galaxy, for example, next. Right, for example, that one, what we will do is subtract each model from that galaxy. And next, what we will have is a cube of residuals, something that looks like that. If then we can measure that residuals within this extractor's mask, and we will end up with a cube of chi-squares. Next. We can use that, for example, to select the models that best fit, which will be the one that minimizes this chi-square. Next. And here, for example, you have the galaxy, the extractor mask, the model, and the residual. Next. So some pros and cons. As a pro, this is computationally simple. You're just doing matrix operations. For that same reason, this has the potential of being faster with GPU power-ups, using GPU computing. As a con, this is heavily dependent on extractor. All of the preprocessing is currently done with extractor. Also, the accuracy is limited by your density of models, meaning how many models you can fit in your cube. Within each parameter step, how many models you have. Also, the analysis of the chi-square is not straightforward due to the correlation between pixels. As a work in progress, we are trying to measure the effect of PSF variations across the field. Also, interpreting the residuals, build meaningful quantities from them. Also, we want to do injection and recovery of models to see what the pipeline is really doing. And some science that we want to do is to look for galaxy cluster. The idea is that early type galaxies will be better fitted by this algorithm better than spirals. So if we find a lot of early type galaxies together, we might think that's a galaxy cluster. And if we have the sizes that we measure for those, we can work with Cormende relation, size versus magnitude relations. Thank you.
Okay, thank you very much, Cristóbal. So the last talk of the session is going to be given by Preethi Nair, and Preethi is going to tell us about a new visual morphological catalog of 113,000 galaxies.
Hi, everyone. So I'm at the University of Alabama. And for those who know me, I've already created a catalog of 14,000 galaxies about 10 years ago. And I hope that would be the last large local catalog I'd have to create. But it turns out that I actually need more galaxies to do some of the science that I really care about. So I created a catalog of 113,000 galaxies, which is basically all galaxies between redshift of 0.02 and 0.06, where I think we can do good classifications. And with the stellar mass between 10 to the 9 and 10 to the 12, where with SDSS you can see detail. So again, that's about 113,696 galaxies. A large area of this is actually covered by the NOAO Legacy Survey, which used the 4-meter decals and MZLS telescopes to image quite a large area. And so in this catalog, I've classified galaxies based on tidal signature. So if they're remnant galaxies, post-mergers, if they have dual nuclei or they're closely separated, those tend to not tend to have spectra of both nuclei from SDSS because they're too close. And then features such as bars, rings, spiral arms, any other low surface brightness features. So I show 4 examples here. And in the left top, you see what I call a post-merger remnant, where it has shells and tidal tails. And then on the right, you see 2 galaxies that are interacting. And so they have 2 separate nuclei. Right below that, you see a typical barred galaxy that also has rings. And then the last galaxy shows something that looks like an elliptical galaxy with blue low surface brightness accretion. You see it in the color image. You don't really pick it up in the individual R and Z images. You will see it in the G-band image. And so I'm trying to find all these different criteria. I've also distinguished between ES0 galaxies, but I've not classified galaxies as SA, SB, all of that yet. I was going over these fine structures first. Next slide. So from the previous slide, I have different science cases involving each of those type of galaxies that I talk about. But one of the main ideas is to use this catalog to calibrate quantitative morphology measurements. Because basically with machine learning, you actually need quite a large volume to parameter space. And my original catalog did not have a lot of dwarf galaxies, and it was missing different types of galaxies. I won't go into the morphology measurements right now. I will say that we can talk about that at a future talk. I will be using this catalog to also verify public morphology catalogs, either through visual or quantitative machine learning methods, so Galaxies U2, or machine learning like Dominguez Sanchez's catalog. So here, this table is showing an example of what happens. So it shows Galaxies U bar classifications, and you'll see if you choose highly inclined galaxies at all masses, and I take a bar probability of 0.8, the galaxies you catalog, for those galaxies that they classify as barred, 81% of them I do also agree are barred. However, that's only 31% of the population. And in that population, they also then have about 19% contamination. And so depending on the bar probability you use, you have different accuracy, different completeness, and different contamination. And it turns out to be mass dependent. So when I release my catalog, I won't release all of it. I'm keeping a part, I will keep a part that will be used for blind verification for any future machine learning or visual catalogs for comparison. Last slide. So I just wanted to show one really quick, interesting result that my student and I are working on. My student is Kavya Mukamdan. So here we looked at bar fractions in the Local-Do universe, and here we're specifically focusing on the area that overlaps with the alfalfa fields. And on the left, you see bar fraction as a function of stellar mass. This is again all galaxies in the volume, and that I have redshift, another caveat, but that's nearly still all of them. And you see bar fractions are bimodal, similar to results that I'd shown early in 2010. The interesting thing that we found was that if you look at those galaxies that have H1 detection that are on the left versus those that don't on the right, you see the overall bar fraction is quite different. And so that's showing some really interesting trends. These bar fractions depend on H1 content. And even the trends on galaxies that do have H1 depend on H1 differently. This is just to show what you can do with such large catalogs when you have the volume. So I'll stop there. Thank you very much.
Thank you very much, Preethi. Let me just stop sharing my screen. Okay, so please show your appreciation for all our speakers in this session. Use the reactions, and then you can clap. Good. So over to you, Benne, for the questions.
Right. It's just my questions at the moment, so please put something in either the chat room or in Slack. Otherwise, I'm just going to ask the questions that I had still left for the speakers. So, Lior, yay! Can you describe how you control for multiple testing when calculating the p-values? So, Lior Shamir, do you have an answer for that?
Well, I don't have that many tests there. Depends on the experiment, actually, which is a good question. It is a good question. So when I do have multiple tests, and sometimes I do, then I use a Bonferroni correction. I just apply a Bonferroni correction. I know it might be conservative, but I do it. Let's say for the slide that I showed in the different for the different parts of the sky, then I apply Bonferroni correction. For the distribution for the dipole or quadruple fitness, I use chi-square statistics. So so everything is just one experiment. So I don't need to correct for multiple tests.
Does that answer, Chad? Does that answer your question?
I'll be happy to tell more.
Sorry, can you hear me?
Yes.
So I mean, given that I don't completely understand what you did, I mean, it was but as you search over different orientations, aren't there implicitly a bunch of different tests being performed simultaneously, right? You're looking over all directions, trying to find the one which maximizes the effect. Is that correct, or am I mischaracterizing?
Well, in some of the experiments, that's what my first experiments were exactly like that. So I separate the sky into several regions. I separate the sky into several regions, and then I test for the probability of the binomial distribution. And that probability, after I compute that probability, I apply a Bonferroni correction in that sense. And then I have other, so you understand now what I did?
Yeah, that makes sense.
And then, so that's part, these were my early experiments. I still do them, but they were my early experiment. The other things, like those maps, they're produced by fitting the cosine dependence to with its chi-square fitness to cosine dependence. So for each a combination of rate ascension and declination, I compute the chi-square fitness to all galaxies in the dataset, the largest dataset of 170,000 galaxies. And from each point, so it's a computation, it takes like, for a single processor, it takes a month to compute that. And then, but it's a single, and then finding creating those maps, but then taking the, but it's just one test because it's the same galaxies that I'm using in all those experiments. So it's just one test, and it gives a pretty smooth map with a fairly consistent, with consistency in different parts of the sky.
How much do you expect the LSST or Rubin to improve your measurement here? Is there an estimate? 70,000 too?
No, it's going to be dramatic because it covers more sky and it goes much deeper than Sloan and Penn stars. I do have some data. I didn't show it. I have some data from Hubble Space Telescope, but the fields are obviously not as broad, but it's deeper. But the overall number of galaxies is smaller. But with LSST, with the Rubin Observatory, you get deeper, not as deep as Hubble, but much deeper than Sloan and Penn stars, much more sky. It's going to be completely different, and that's going to give us an answer, I think, to that question.
Okay. This is like a general question also for the other speakers. So, how does Rubin change your science? I think since everybody has, or well, who wants to answer that first?
So in my case, rather than changing the science, it's sort of like a new challenge for the algorithm I'm working with, because there will be massive data sets, a lot of galaxies. So it's rather more like a goal to be able to classify all of these galaxies to get measurements as fast as possible. And also the depth is, I think the most important is the depth, that we will be able to find galaxies, get measurements for objects that are way fainter than we're working with now.
Preethi?
I mean, statistics is obviously one. I mean, like how well you can constrain results is an issue. So like with looking at whether close pairs trigger bars or AGN, you need a lot of close pairs. You need to know, you need to identify these systems in different ways. Larger area always helps. Better depth helps if you to figure out things that are tightly interacting. And finding rare galaxies. There are a number of really weird objects. And the larger area you have and the better depth, you can actually find these systems. And so there's just a lot that we can actually do. And the way that LSST is doing things with time domain, especially with tie-ins with other surveys, I'm especially looking forward to something that'll happen with eROSITA, because eROSITA will eventually release all sky surveys of X-ray catalogs that'll be sensitive down to 10 to the 41.5 erg per second, where you'll also have imaging and pretty good resolution. That will be really, really interesting to study how AGN are triggered when you know the structure of the galaxy as well.
Any more questions? Yeah, statistics always good. I don't have any more questions here, except that I have my own questions. So I'll run to those if I have to. But does anybody have any more questions for our speakers?
I had one that I posted this in Slack, and I'm happy to take the answer on Slack. I guess I have a few questions for Nushkia, but I will go read the papers first and maybe save some of those questions till later. But one simple question, I guess, is how sensitive is the determination of the radius that you have defined, that R1, to the background subtraction? Is the radius that you're trying to measure typically near the sky background level, or many sort of magnitudes above that sky brightness level?
Thanks for the question. It depends on the galaxy. So it depends because, it depends on the color, and it depends on the quality of the data as well. I think I mean, I've seen the HSC data on the platform, and it's worrying because you clearly see that's completely over subtracted. And the images I'm using are actually very well treated for low surface brightness. It was reduced specifically to preserve the low surface brightness feature. So it's a good data set I'm using. We actually, in the paper, compute the uncertainty due to sky subtraction. I don't have the number at the top of my head, but it's small. I mean, it's not crazy. And it could be also because I'm using very good imaging.
Yeah, actually, it'd be interesting to know, I guess, if you could compare the same galaxy from your previous work to what the stack is doing to HSC data, just to see like how much.
Why not? Sure. I mean, I'm now that I have direct access to everything. Sure. I just haven't had time because I actually just 2 weeks ago I defended my PhD thesis, so I haven't had time. Thanks. I haven't had time to do much more. But yeah, I mean, now that I have access to it, I will. We can do that.
Yeah, it'd be cool to see. Thanks.
Yeah, no problem.
So Benne, I think we were asked to sort of wrap up around 45.
Perfect.
So unless anyone has any more burning questions, I guess we can. So thank you all for coming, and thank you to our speakers for giving their talks twice and both times keeping to time. And thank you all for your questions. So enjoy the rest of the conference, and thank you again.
And thank you to the
Thank
chairs.
you. Thank you very much.
Thank you very much.
Thanks, guys.
Bye.